appreciate the time everybody's taking to come here. I think we have a very esteemed speakers on this panel. Zhi-Li will go ahead and introduce them in a bit. But today we essentially want to discuss everything about how we can use data and machine learning in networks. And from my perspective, so I lead a team at Juniper Networks, and we look at some of the cutting edge technologies that we want to use and the use cases that we want to bring to our customers with the help of ML. So I have a team which looks at data analytics in both service provider networks as well as data center networks, and I'm looking forward to I would say a healthy discussion around all the interesting challenges that we have, because there are a lot of different areas that we can go into, and we have esteemed panelists over here who have presented some of their work, and we'll give them each 10 minutes to present. And then following that, we'll have a Q&A session. So one request I have for everybody else would be, like, if you have a question that you would like to ask, you can easily pop down into the chat window, and then we'll be taking them in the order that they are received. So again, welcome everybody. I hope to have a great discussion. And Zhi-Li, do you want to go ahead and start the introductions?
Great, thanks, Harshit. So we have a full distinguished panelists from both academia and industry. So alphabetically, we have Nirmit from IBM Research, and also Professor Sumi Helal from Lancaster University. He's also from University of Florida, and he's still just finishing up his class. I think he just joined. And Professor Xin Liu from UC Davis, and also Sayandev, Mukherjee from Cable Networks. So I have a slide to briefly show you each of them, their background. So first of all, we have Dr. Desai. He's a principal research scientist and manager IBM Research. So his mission is to develop practical solutions to hard problems and test them in the real world. So here, I'm not going to read through all the slides. You can actually see his background. He got his PhD in 2007 from NCSU, and he's interested in applied edge AI and edge infrastructure. So next we have Dr. Sumi Helal. I'm not sure I say the name correctly. He's a professor in the computer science at the University of Florida. He's also chair in the digital house in the University of Lancaster University. So in particular, he's interested in looking at the fundamental problem in IoT smart spaces and mobile computing. He's also interested in applying those issue problem to digital health, aging, disability. Right? So applying data-driven approaches to solve these problems. And next we have Professor Xin Liu. She's a professor at the computer science at UC Davis. And he has been a professor at the UC Davis for many years. Before that, he also worked at the Microsoft Research. And her interest is the wireless and cellular networks, in particular, apply data-driven machine learning approach to solve these type of problems. And we particularly thank Professor Xin Liu to agree to serve on the panel. We want to avoid having a manual, so men-only panels, and Professor Xin agreed to serve on the panel. So lastly, and but not least, we have Sayandev from Mukherjee. He's a principal architect in the cable networks. He got his PhD in 1997. So on his LinkedIn pages, he actually listed his PhD thesis. So he did his PhD on neural network training, and also master thesis about gradient-based neural network. But before all the AI neural network become popular in the networking, so he did this in 1997 or earlier. So he had many years at the work at the Bell Lab, where he worked on a number of different industries, had more than 20 patents. So again, he's interested in applying machine learning, deep learning to wireless networks. So we're going to actually start we're going to have each of the panelists to spend about 10 minutes to talk about the experience applying machine learning to networking related problems. So we're going to actually start kind of reverse alphabetical order. So we're going to have Dr. Mukherjee start first, and then Professor Xinyu, then Professor Helal, then lastly the Dr. Desai. So I'm going to stop sharing. So assume each of you actually want to use your own, drive your own slides, right? So Yang, I can stop sharing.
Okay.
We're getting started.
Very well. Thank you, Zhi-Li. I'll start sharing now. Okay. All right. So let's go to that. And thank you. I'm going to give a very brief overview of some of what we think are the principal challenges for deploying machine learning and integrating machine learning into network operations. Okay. I don't think anything on this particular slide will come as a surprise. This is just a set of excerpts of news articles from here and there, but it basically talks about the explosion in the number of cells that 5G will bring. And it's actually not just the number of cells, it's the number of different services and the variety of devices that are going to be connected to 5G networks. As you can see, the CTO of Nokia was talking about how private wireless networks could be twice as big as commercial wireless. That's another issue. Nonetheless, it's quite clear at this point that deployment and operation at this scale will require automation, right? And the existing pool of human experts is not big enough. Moreover, there will be new entrants into the space that are not traditional mobile network operators. These new entrants most likely won't have the teams of experienced network ops engineers that the traditional well-established MNOs have and have had. While they will be dealing with networks that are more complicated than those the traditional MNOs have dealt with so far. So network planning, fault prediction, coexistence with previous generations, or and all of that at scale, right? So we believe, and by now I think this feeling is pretty universal in the industry. Um, uh, you know, operation at this scale will require machine learning. Of course, the eventual goal is to go toward full automation, or at least as close to full as is possible. Fully autonomous networks that can configure, optimize, run, and heal themselves with little or no human intervention. And to see an example of all the um, applications of machine learning in a 5G network, take a look at these IMT 2020 goals that I extracted from a recent, very thorough tutorial overview paper. And you can see in there the extent to which the boundaries of the previous IMT advanced have been expanded to generate the boundaries of the requirements for IMT 2020. That's in the central figure there. And on each of the corners of that central figure, you can see the sort of criterion in which the boundary of IMT advanced was expanded, and also a representative selection of machine learning based techniques or proposals to get to that expanded boundary. Now, one very important thing to bear in mind in 5G networks, or indeed any kind of network, actually, even 4G today, is that if you are to maintain privacy of, for example, user data, things like that, or even if you want localization to a specific environment where a small cluster of cells is located. You probably want to train on local data without moving that data up into some cloud-based server farm. In fact, that is not going to be easy to do on a wireless network anyway, because as presently provisioned, the backhaul is very congested. Um, but this larger issue can be largely tackled using federated learning. It allows for collaborative training of a single global model. And as you can see over here, these local learners are training local copies of that same model on local data. So that allows for localization, personalization if the local learner is on a single user device. And only the parameter updates are sent up to some central controller, which then weights them appropriately and applies the parameter update to its copy of the global model. And that global model can then be broadcast to each of the local learners. Now, whether the global model should be used to completely overwrite the local learner's model or not, and if not, to what extent, that's an open research problem. So this is just one of many fascinating problems that arise when trying to handle these various sets of trade-offs. Moreover, we have the issue that the presently provisioned cellular networks not only are tight on backhaul capacity, they're also constrained in terms of compute and storage capacity. I mean, you may see this as an argument to go all in on additional edge computing resources. And indeed, that's a strong likelihood. But on the other hand, cloud-based computing still has its place and it is much more powerful. So a proposed solution could be hierarchical federated learning with split learning. Split learning is another method whereby for a complicated model, I'm thinking of a multi-layered deep learning model. Some of the lower layers could be processed locally with the upper layers being combined across local learners and located either at an edge computing resource or even up in the cloud. So as an example, we can have something like this. You have federated learning between DU1, 2, and 3, but on the other hand, DU3 has enough compute and storage resources to hold all four layers in this toy example, all four layers of this neural network model. DUs 1 and 2 can only hold the two lower layers, but there is an edge computing resource that holds a combined higher two layers for both DUs 1 and 2. So you have both split learning between DU1 and 2 and federated learning at the overall level between DUs 1, 2, and 3. Moreover, there is the major challenge in wireless networking with collecting labeled data. In some circumstances, it's available, but in others, it is not, and you have to launch separate dedicated projects in order to collect that labeled data. And then curation and labeling and cleanup will take even more time. So it is desirable to be able to train on data as it comes in without needing to label it. And one way to do that is through reinforcement learning. Of course, reinforcement learning has multiple challenges of its own, which I can talk about later, should there be questions. Um, I'll just point out here that a popular reinforcement learning algorithm named A3C, asynchronous advantage actor critic, maps quite nicely into the federated learning paradigm. And in fact, it can even allow hierarchical federated learning with split learning. And finally, to conclude, I think if you are to deploy all of this, you need a machine learning as a service platform that can handle the end-to-end model lifecycle. So from data collection, ingestion, data cleanup, feature extraction, should you want to do that to apply classical machine learning models, followed by model training, followed by deployment, and then model monitoring as of the deployed model to be able to decide when the model needs a tune-up, when it needs to be refreshed, and when it should perhaps be retrained all over from scratch. Moreover, the split and hierarchical model training across all available resources, in some region of the network, presents an interesting challenge of its own and is probably best tackled with some sort of an economic model and utility functions for situating parts of the model and performing certain computations in certain resources. So to summarize, wireless networks come with a unique set of challenges. They have communications constraints, computing and storage constraints. The usual IT-centric model is not directly applicable to a wireless network. I hope that, if nothing else, is now clear. And successful integration of AI/ML into network ops requires ML/AAS platforms and presumably utility-based assignment of computation, storage, and to all of the various resources that are scattered all over the entire network. Finally, I'll say I work for not the wireless industry so much as the cable operators industry, and any lessons learned from wireless will also apply to next-gen cable networks. We don't have the air interface. However, it is still an RF signal sent out over a different medium. That's all. Okay, thank you. And I hope to discuss this more during the panel discussion phase. Zhi-Li, I think you may be muted.
I'm muted. I'm sorry. Yeah. Jing, you want to get started?
Let me share screen first. Okay. Thanks, Harshit and Zhi-Li, for the invitation. It's going to be a fun panel. Just look at the topics here. Zhi-Li and Harshit sent out a list of questions. So more or less, my slides are organized based on their suggested questions. So we have been working on data-driven networking for a number of years, touching on different topics, resource management, mobile system personalization, encrypted traffic classification, etc. And today I'm going to talk about one topic, cellular configuration. So let me first start with Zhi-Li's first question. What do we see as opportunities, as challenges? So I see networks when meets machine learning sees a lot of possible opportunities. Basically, networks are largely engineered complex systems. Because of this complexity, it's beyond the white box modeling that we are used to and what we have been relied on. And also the environment of wireless network is highly dynamic, and most of them are partially observable. In all layers, we see people have trying different type of machine learning algorithms to solve complex problems like adaptive modulation control, MAC layer routing, TCP, virtual bit rate allocation, etc. And we also see all players in networks considering machine learning as possible their solutions, from operators to users, content providers, etc. We also see a lot of different objectives can be studied using machine learning algorithms in networks, from network users like churn, fraud detection, network services, and both existing networks and new architectures, as well as new deployment, as mentioned earlier. At the same time, I also want to mention machine learning is not a cure-all. We have worked on machine learning for network for 6 years, and I have to be honest, half of our projects are successful of somewhat, and the other half are just not suitable. And gradually we learn, well, not everything is suitable, and it's a good idea to start thinking, why is it suitable? I'm going to talk about that a little bit later. So Zhi-Li asked for specific examples, so we are going to just use one case study. In this particular case, cellular network configuration. In cellular networks, cellular base stations have a large number of parameters to configure, and usually in the range of a few hundreds. That includes transmission power, pilot power, threshold for handovers, etc., etc. And also, network operators have many performance metrics and sometimes conflicting, ranging from total throughput, average data rate, or edge user performance, and so on. Let's just look at a concrete example. A2 threshold RSRP is one particular parameter defined in LTE. Basically, when camping on a cell, a UE keeps monitoring the signal quality that is received from the serving cell. Once the signal quality of the serving cell is worse than this particular threshold, the UE starts to take measurements report and send the information to serving base station so that they can identify a target cell and prepare for handover. So when this threshold is too small, this handover is very hard to trigger, and possibly the user could lose coverage or connection. But if the threshold is set to be too large, then there will be a lot of signaling between the user and the base station, and with a lot of resource in this case. So, and there are many, actually just for handover, there are many other thresholds that need to be tuned. So the traditional approach is basically field engineers go into the field and start with a default value. If nothing breaks, they will just stay there. The default value will be used. If something happens, there's outage and performance degradation, then the field engineer will try to fine tune it. This is very expensive. It may take hours or days to tune a parameter, and usually a field engineer can tune 1 or 2 parameters each time. Remember, there are hundreds of parameters to be tuned. So as a result, most cells just set the default configuration. And this gives an interesting problem. We have a lot of data because there are millions of base stations in the world. But still, we have a cold start because most of them share the same configuration. So our study looked at how to use machine learning-based approaches to automate this process. This is again mentioned by Sayandev. We want to automate the process because of the scale. We have a number of challenges here. The first one is what I said earlier. There are a lot of data from different base stations, but we still have a cold start because most of them are using default values. The second challenge is network performance is a highly complex and noisy function of the configuration and cell states. So to measure the performance takes time. And usually operators are risk averse, and for a good reason. We want our cells to work well, right? So usually we have a limited configuration adjustment frequency because the data is very noisy. So in a field experiment, what happened is maybe 1 adjustment a day. And usually there are limited durations because base stations want to operate in a stable format. So we have worked on this problem for a couple of years, and we have developed multiple approaches to address this problem. Our first approach is a prediction model-based optimization. Basically, we trained a neural network model to predict the performance of the cell based on the configuration. Then we optimize over the entire network to consider the interference between users. This was done for pilot power configuration. We tried this on an industrial grade simulator to evaluate the performance. Our second approach is to look at multitask learning. We developed kernel-based contextual bandit to solve this problem, to look at the similarities between base stations, among base stations. Our third approach is a collaborative learning-based approach. Basically, we consider cells, they have a similar component that can be learned together using old data. And then each cell has a separate residue component that needs to be learned individually based on the cell's own data. This is an approach we actually made practical. In a sense, this was implemented in real operation networks with 1,700 cells, and we see a 20+ improvement in KPI. And taking this work further, we got some theoretical inspiration from this kind of data scarcity issue. We actually look at an algorithm called opportunistic learning. In classic machine learning algorithms, in bandit and reinforcement learning, we usually have the assumption the exploration cost of a suboptimal action remains the same. But if you look at network configuration, you can imagine what I do at 2 a.m. when there's very few users. The cost, if my action is not optimal, is actually very small. So we took this idea and we call it opportunistic, and we studied a number of algorithms in that and took into the machine learning community. So let me summarize the typical steps we look at and how a machine learning, how to use a machine learning to solve a particular networking problem. The first question, we learned this the hard way, is to ask, why is learning a suitable approach? We learn not to use machine learning just for the purpose of using machine learning. Of course, machine learning is fancy, but let's not do that just for the purpose of using it. We really need to carefully evaluate existing approaches and understand where can machine learning help and why can machine learning help. And also, we want to look for problems where there is room for improvement. So for example, I'll give you a field attempt. We look at MIMO configuration in one of the earlier work. Then our results were actually not very good. Then we realized this has been studied very extensively in the physical layer communication research community, and the heuristic algorithms work really well, and there's very little room for improvement. So no matter how good your machine learning algorithm is, then if there's no room for improvement, it's not a suitable attempt. Then we look at problem abstraction and formulation. So for example, in the cellular configuration example I discussed earlier, we tried many different ways to formulate the problem with different levels of abstraction. That will significantly affect the model complexity and how much data you need and how do you evaluate and so on. This is where domain knowledge can be really critical, deciding the suitable problem formulation, state, and abstraction. Then there's data collection and data cleaning process, and then we look at the machine learning algorithm. Sometimes this could be the easy part. Sometimes we can use existing algorithm almost directly. Sometimes we have to twist it, and sometimes we have to develop new algorithms. And usually this has to iterate with data collection and evaluation. Then the last one, not the last one, this, as I said, should be iterated, is how do we evaluate this problem? And sometimes evaluation can be really challenging. So this is my last slide. Going to the last question Zhi-Li posed there. So what are the gaps and technical challenges? Data availability is one big challenge, and this probably will be mentioned in multiple places. And another challenge I really want to bring to the table is sample efficiency. That basically means depending on the algorithm you choose to use, there might be a large number of samples, data samples needed. So for example, cellular configuration is a case where sample efficiency is very challenging because we don't have a lot of data. So we really have to use this data effectively. We study deep reinforcement learning. I know Zhi-Li studied as well, and Sayandev mentioned the reinforcement learning. Deep reinforcement learning is very data hungry. Where do we get enough data to develop a good algorithm is a challenging issue. Also in networks, we most likely are not going to let a black box of machine learning model run our operation. So interpretability, safety, security, and user privacy are all highly important issues if we want to put this into real practice. In terms of whether existing machine learning algorithms suffice, we have seen cases where we can directly apply existing algorithms, and we have seen cases where we have to twist existing algorithms in an unusual way, and in some cases we have to develop new algorithms. Last is, well, we have to think about why a learning-based approach could outperform an existing approach, because they don't always outperform. So that's my last slide. Thank you very much.
Great, thank you.
I'll stop sharing.
Sumi, you're the next one.
Zhi-Li, just sharing, make sure I get this done right.
Yes, I can see you. You can. You should be able to share.
Yeah, I'm trying to share here. It's asking me if I want to share the entire desktop. Let me try again.
There's a menu in the top. You can choose a certain application, not the whole desktop.
Okay, let's see here. Okay, you are still not able to see it. Is that correct?
No.
Okay. That's interesting. Never had that challenge before.
When you press the share button, it will open like a dialog box, and it should be on the top of that dialog box like a tab. They are not really query tabs, but you see in the middle one is about filling just one application.
Right. So if you still have a problem, I can use the slides you sent to me.
Well, why don't we do that, Zhi-Li? If you can please put the slide, that'd be great.
Okay, just let me know when you want me to.
Okay, I'm ready.
Next slides.
Yeah.
Just one moment. Go find your slides. Somehow you always the wrong slides. Sorry for the technical issues here. Okay, I think this is.
That looks like me.
Yeah, okay, great.
Okay. Thanks, Zhi-Li, Tamer, for inviting me to join this panel. I have 10 minutes here, so I think, Zhi-Li, I have to tell you to go to the next slide then.
Yep.
So sentience efficiency, the issue is how can we do machine learning, but in a sensible way. The idea that we have big data and we're able to look at the opportunity of learning from it, this is great. But in actual deployments, we have seen and we have listened to Sayandev in his first talk saying that the idea of going and doing the ML in the cloud is most likely not going to be the way to do it. We have to do some federation a little bit. So that's absolutely true, because living up all this data is going to be very expensive. And the key question here is we're not sure all the data is needed. So if we are adding a specific data item, does it really make a difference? In other words, if we have data and we're looking at it and we're arriving at some conclusion using machine learning techniques, what if we take 25% of the data out and arrive at the same conclusion? What if we take half the data out or still arriving at the same conclusion? Then we haven't been very efficient in our sensing and our inclusion of data. So we need to know which data is influential so that we can successfully select it in our data acquisition and apply it in the machine learning. So we need to learn how to be sentient efficient, not just energy efficient. Next. So to explain this in actual context, I would like to bring in the application area of large scale cloud edge IoT architecture, meaning large smart city deployment where you have cloud services where the applications are and all these devices and some edges in between. Next. So just to make sure that discussion is also grounded, every sensor devices that generate data is attached to a platform to just make it smart, meaning you're able to get right to that device. There's edge and there's a cloud. So when the application on the cloud increases, that represents some kind of a vertical growth where you have more pressure on the system to access the services and to access the devices. But if you have more deployment in the city, more devices, more smart meter, more parking lot sensors and all that stuff, that represents a horizontal growth, and that put pressure back on the cloud. So you got these two sources of pressure: application on the cloud, putting pressure on the devices and their operation, for example, their battery, and the increasing horizontal growth in the city, putting a lot of pressure on the cloud. Next. So we have two key challenges here to look at. The first is how to conserve the energy of these devices. Fast burnout of these devices will render these devices useless, and services of the smart city will not work, and the citizen will lose faith on these services. The second challenge is how to run the smart city in a fixed budget. There is no concept of elasticity in the mayor office. Municipalities have fixed budget. So you cannot say, I have $3 million for Amazon, but that can go up to $33 million for Amazon. It's impossible. You have to have a fixed budget. So how can you run the cloud on a fixed budget? That means how can we control the elasticity of the cloud, restrain it so that we can stay within budget in face of the growth in the city. Next. So the first challenge, and now you're going to get to start to see the sentience efficiency and the need for it. But the first challenge is that we have got to reduce the use of energy of the devices, regardless of the scale of the city. And we cannot do this by optimizing sensing energy efficiently alone. We have got to look at the applications and the use of these devices and their data. Without having a view of the application, we will do our very best, and that would not be good enough. Database researcher figured this out. We're staying still with challenge one, please. Database researcher figured this out a long time ago but on the space of database, and they refer to this problem as redundant data acquisition, and they try to minimize such redundancy. Here we have a very similar problem that is left unaddressed, and in a very large deployment, or if you have a huge neural network model that is running, like Sayandev mentioned, and that model, just all its pieces are demanding the data without knowing what the model is, without sending a piece of that model to the federated elements, part of the network. Without doing this, you're going blind, and you're just leaving all this data up, only to discover what you need and what you don't need up there in the cloud. Too late. It's too expensive already. So here we have to optimize by involving the application in the optimization problem to understand what data need to be lived up to the analysis and what data should be left untouched. Next, please. The second challenge is the cloud affordability. And the idea here is there's significant attention, not only per device or sensor, but per their duty cycles. So millions of sensors produces billions of interactions, and billions of devices will produce trillions of interactions. So that is enough to take down the cloud and make it extremely expensive. So what we've got to optimize here is we have to restrain, we have to put a restraint and sort of work within that restraint. So we have to apply constraint problem solving on the cloud. In other words, we have to do everything we can to not sense what is not needed to be sensed. We have to be sentience efficient. Next. So the overall approach is to try to minimize all movement in all activities in all directions. And that is anti-stream, people who like stream processing. Here we're saying, weaken the stream. We don't want streams. We want some very weakened streams. You try to figure out somehow, only the most surprising data in the city need to be perpeculated up to the edge and to the cloud, but only the most surprising. And inverse-wise, the most curious and itchy bits of the application or the model, the machine learning models, the most curious parts of that application are the ones that need to sort of go down closer, go down to the edge, and even to the devices, as I have shown you. That put a pressure or put a constraint on what application models we're talking about. We must necessarily be talking about a spatial application model, one that the application can be cut and diced into pieces. Indeed, that's a constraint. We need to use edge strategically to learn and consolidate knowledge about the data below and the application above. We can even get aggressive to use the edge as a satellite baby cloud to the mama cloud. Make the edge a super edge by getting it to actually be outsourced to by the cloud to do things that are easier for it to do and are more powerful for it to do, even though it's no cloud. But using the edge as a super edge is going to also help significantly. And by actually using an edge, that means as far as the cloud goes, it doesn't know. So that's also sentience efficiency for the cloud. It doesn't know what's going on. It's outsourcing to the edge. Finally, we have got to apply sentience efficiency before energy efficiency. So before you try to do anything energy efficiently, ask yourself, did I even need it to get this sensor value at all? It's not enough to be energy efficient. It is first necessarily to be sentient efficient. Next, please. That's an example here to show you the idea of manipulating the stream and not have everything to be a stream. So that's a push-pull envelope. By observing the application and the data nature and the characteristic of the data, we should be able to vary that envelope of who should be pushed, which data should be pushed, and which data should be left for a pull if needed, when needed. That's, again, sentience efficiency. Try to not bring everything. Try not to feel like you need everything. I can just skip now and go to the next slide, please. So to do sentience efficiency, we created a waterfall cascade of optimization algorithms. First one is application fragment caching algorithm, meaning decide which part of the application in the cloud among all the applications in the smart city better be delegated down to their super edge. And to do that, you have to cut that part and send it down. And that edge may not have the capacity, so you have to do a replacement if needed. That's AFCA 1. And then we move into sensory energy challenges, where we try to, again, not know as much. So the first thing we did is a branch permutation shortcut algorithm. The idea is to look at all the application collectively. And by looking at them, you are able to actually do some shortcut analysis, similar to what we have done in the old days for compiler optimization, and decide that, you know what, I don't really need to get this data. I don't need to contact that sensor. I can skip the entire sensor under one edge. All that's not needed, because by looking at the eventual utility of all this, the applications, I don't need them. I can see from the application mix that will not be useful. So why even sense it in the first place? So that is a BBA shortcut. AFCA 2 has similar thing, where you try to also offload the super edge by pushing down further to the sensor. And then finally, AAAS is the application-aware adaptive sampling. That is basically ARMA. And many of you know about ARMA, the adaptive autoregressive moving average model, very successful model. But actually, we have shown that you can even beat ARMA. You can do much better than ARMA if ARMA include characteristic information of the applications, not just data characteristic. So the combined use of both apps and data is crucial. Next, please. We can just summarize the slide saying that the system dynamics should always include data and application changes, and basically running these algorithms. So this is a distributed optimization, because you have multiple algorithms that actually interplay with each other. Next. Here is just to show you some of the effect of applying this Sentience-Efficiency algorithms. Here with the horizontal growth of the smart city, we are able to sort of slow down the expansion of the cloud. And you can see from this data, that was done in ECU, in number of ECUs on Amazon Cloud. Next. We can also see the impact of vertical, pumping more application. That's a vertical growth, putting pressure on the devices. How are we able to, again, use less of the cloud to achieve this, and how we are able to save energy on the devices. Next, please. This is the energy saving part I was talking about when you apply all these algorithms combined. So I'll just refer you to that top chart. You can see here the blue is just grouping. So like group 2 is adding shortcut with group 1, which is no optimization. 3 is adding permutation. The fourth one is adding AAAS, so it's everything else together. So group 4 is a green, and you can see here the energy saving. So this is a hefty 34% saving in energy when you apply this optimization. When you try to not know, not sense what is unnecessary, then you're able to make all these savings, and you're able to make the cloud sort of work on a shoestring. Next, please. So to close here, the lessons we learn is that sentence efficiency is very important, not just energy efficient. Do the machine learning, but do it over the leanest, most influential data. Don't get so excited and collect all kind of data in the world so that you arrive at a conclusion. That is not the most heroic thing. Most heroic thing is to prove that you're able to do that on the leanest amount of data. I'm not done yet.
Hello?
Yeah, Zhi-Li, I'm not done yet. I was in the middle of the last
somehow there's some problems. The screen sharing just stopped.
Oh, I'm sorry.
You still want the slides?
Yes, please.
I'm trying to bring it up. Just give me 1 second. Not sure it's my computer. Okay. Okay.
All right, thank you. The second lesson we learned is that we have to contain the cloud cost. So you need to slow down the cloud, the machinality. Don't be excited that the cloud is elastic because somebody's paying for this. So the cost of real AI will come to limit AI. So prepare to do AI on the cheap. Again, by doing your best and proving that you're bringing only the most influential element in the analysis. That's important. Finally, consider both the data and application combined. In everything you're doing, the data and the utility of your analysis, not just the data. Like, what is the utility of the analysis? That's the application. They need to be considered combined because that's where the magic and the reduction would be. Finally, we have to build systems that really involve system people and optimization people. Optimization and system people are never in the same space. We now need to create systems that involve both of them, where the optimization is embedded deep into the system. That has to happen. Finally, here, optimization-friendly applications are needed. So we need to figure out of application models, like functional programming might be very useful because it's a diceable and breakable application model. So all of a sudden, I see value in functional languages and functional programming model. But we have to create something where we're able to cache a part of the application down as we cache data up. Thank you very much.
Thank you. So last but not least, we have Dr. Desai.
Yes, let me share. No. Okay, do you see my screen?
Yes.
Going in the full screen mode. Okay. Hey, everyone. So it looks like there is a lot of agreement among, what Sayandev said, what Sheen was saying, even what some of the points from Sumi. So I'll see, and my own pitch here is quite similar. And in the interest of time, I'm going to focus on the differences rather than go over everything. But you've seen my introduction, and mostly I'm going to talk about the edge AI, which is what we call edge AI is basically the problem of dealing with the fact that there is going to be many edge locations in a given context, in a given application context. There is going to be data on all of these edge sites, and you want to apply some of these machine learning techniques that we are all familiar with in this setup. And what are some of the challenges that come up, and what can you do with it? And in my own work, we are an industry research lab, of course, so we try to solve some of the interesting problems and deploy them in the real world scenarios. I'm not going to talk much about the edge infrastructure piece here, but there is work you can check out. It's into a couple of offerings and products out there in case you're interested. So why do we talk about 5G and edge and AI in the same breath at all? Like, they seem to be pretty distinct concepts and trends. Why combine them, right? Why is everyone combining them, or why are we combining them when we say edge AI, right? This is just showing you a typical 5G deployment picture. And Sumi alluded to this earlier when he said the private 5G is going to be double the size of commercial 5G. What that means is that there is going to be these commercial buildings, office buildings, retail stores, hospitals, what have you, where there is going to be this green area that is new compared to what we had in the 4G architecture. So there is an additional control point in the form of an edge server. You can call this mobile edge compute box. Various companies, at AT&T, Verizon, Vodafone, they call these different things. But at the end of the day, there is a local telco managed server that applications can be deployed onto, and both telco and the owner of the commercial building, could be Walmart, right? Could be an IBM office for all we know, where applications can get deployed. They partner on this, and they control what application get deployed where. So this is a very concrete development. This is why the 5G architecture, because of the small cell and so on, it's going to lead us to a concrete future of edge computing, where there is going to be a large number of such edge servers deployed by telcos and used by companies and users of these applications. And then AI is simply the most common application, right? So most common workload that you're going to run on these servers, because whenever you're looking at edge computing, you're motivated by the problem of large amounts of data, having to do low latency computations, having to deal with privacy issues, and all of that says, well, that's where edge computing makes sense. So if I have to deal with large amount of data in low latency fashion and make sense of it, I might do well by applying some of the AI techniques there, right? So that's why applying or enabling AI at the edge is an important area, is an area where a lot of the real deployments are going to happen, and we're going to see significant growth in both business and technical work around that. So that's why we are talking about these things. Now, when we say edge AI, we've seen what federated learning can be. Sayandev provided a nice introduction of what distributed learning in general is. There are many different scenarios that I'm representing here that we would call as part of the whole edge AI spectrum. And when I'm showing a mobile device here, that is just, it could be a mobile device like a smartphone, and there is typically called extreme edge, or it could be a server. So it's a generalizable picture. The mobile is not a constraint, right? It could be hierarchical, like what Sayandev introduced earlier. So, but if you go from A, B through C to D, you see a few things happening. One is that you're applying inferencing on the edge, and that's a common thing. Inferencing at the edge makes a lot of sense, gets around all the issues of aggregating all the data in cloud, the costs, the latencies, the privacy issues, if only you could infer at the edge. And that's the sort of the second part of A. And that's where a lot of the work is happening as well. When you go and look at federated learning, you're talking more about C, all right? You have collaborative training going on across multiple edge sites, and they all have their own local data. They all have their own local context. So they may train a single common model across all of them. The problem with just that, or stopping there, is that each of these edge environments or edge locations are unique. They have a different context. They may be looking, if you have deployed a camera, they may be looking at different kinds of objects. They may be pointing at different kinds of things. You cannot use the same common model across all edge locations and cloud and have good performance. So the domain is an important notion when we enter the area of edge AI and doing distributed machine learning. So there are approaches where you apply transfer learning so that you have a common model, but then you tailor it to local environment, and that's more like B here. The most interesting and the most commonly needed scenario seems to be D, where you have multiple locations, each with its local data, and each not having individually having sufficient data, right? So you don't have sufficient data locally on each of the edge sites to train their own local model, or to even transfer learn from a common model. So what you do is you identify which of these edges, so which of the Walmart retail stores, they have thousands of stores in the US, just taking an example. Which of the stores that they have serve a similar demographic? So they carry similar product catalogs. So they have similar buyer behavior. You identify which are those similar stores, and then you instantiate some kind of federated learning among just the subset of them. So there are multiple such scenarios, and I just wanted to say that when we talk about distributed AI and applying AI across the networks, this is important to keep in mind. So if you generalize that, you come with this kind of a picture where, first of all, any application today, modern applications, they consume cloud services from multiple cloud service providers. So you don't have a single cloud. You may have multiple public clouds, multiple private clouds, and a given application is consuming services and having dependencies on multiple of those. And then you have your company's data center, and you have many regional data centers, either via the 5G deployments like we spoke about earlier, or just by having some kind of compute capacity in your locations, hospitals, retail stores, and so on. And then you have, of course, the devices that actually generate the data at the edge. So there are a few interesting challenges that come up in this setup where you want to be resource efficient. You don't want to be transmitting data unnecessarily. I think we heard about Sentience-Efficiency. This is kind of saying, yes, once you have sensed it, do you really need to transmit it? If in case you ended up sensing it, right? Or could you do something locally? And then you have the problem of selecting the relevant data at each of these edge sites. And it's very similar to the ideas that Sumi talked about. But the difference here is that you have, before you know what data you need, you may need to look at what data you have. So it's a catch-22, right? Until I see what data is coming out of my sensor, I don't know if I am good with sensing it at 5 minutes per sample, or I need to go down to 5 seconds per sample. So how do you control that? How do you select a right subset at an edge location to then either transmit it or to involve it in the distributed learning? So this is a generalized sort of setup in which then I'm going to talk about a couple of approaches and algorithms that we have worked on. One of them has to do with optimizing a federated learning process by optimizing the frequency of updates. So one of the important things to know about federated learning is that in steps 1, where you get a common model from an aggregator, in step 4, where you report your local weight updates to a parameter server, these could be big amounts of data. And if you're doing this in an iterative fashion, you're basically multiplying the amount of communication resource you're consuming. So it makes sense to talk about how frequently do we really need to sync up with a parameter server. Can we get by not frequently not doing it at every iteration? Can we report our weight updates after n iterations, or more importantly, tau time steps as indicated in this slide, right? So I'm not going to talk about specific technique and so on. I'm going to point you to some papers in the end so you can look at it. The other thing is that very commonly, it's a common tendency for some of the image and text and other unstructured data related problems to start with a large machine learning model. Hey, because they work very well, they're very accurate, they outperform human accuracy in many cases, so why not? Sure. The problem with large models, again, is that you're consuming tremendous amount of communication resource, you're incurring high amounts of costs. So can we do better? You may all heard of model pruning techniques, where you look at a model and look at what the data set is like, and then prune some of the nodes out, some of the layers out to make the model smaller, and it is good for many reasons. It's more robust, it is smaller, it consumes less resource, faster to train, and so on, many advantages. But how do you do that when you have data across multiple sites and you're trying to apply federated learning to learn a common model? So federated model pruning kind of addresses that specific problem. The last one I'm going to talk about a little bit is it's another common problem. You typically have, if you are a large company like Walmart, and I'm sorry I'm harping on Walmart, but really this is just an example. You have many models and many applications, and you end up with literally hundreds of thousands of models in your model zoo. You already have, if you look at TensorFlow models, you already have very large number of models that are trained by a variety of teams and communities across the globe. Which of the models at a given edge location should you start customizing or tailoring or transfer learning from? What's the best model to start from? That's not a trivial question to answer. You can apply like a brute force model accuracy evaluation kind of a technique to evaluate all of them and say, hey, this performed the best. The problem with such a thing is that these models are trained with different label sets. They are trained to, say, in an image world, they may be trained to, on the same kind of images, they may be trained to identify cats versus dogs, or they may be trained to identify white animals versus black ones. And so it depends very much on the label set, what the model is trying to solve as a problem. And so the point of model selection techniques is to identify models that are good at discriminating your data set, no matter what their original training set was, or what their original data set was or domain was. If a model is able to discriminate your classes better, then it may be a much better model for you than a model trained on a similar data set. So this is one of those insights that again pans out, and we have experimental results and paper on this as well. So let me pause here. I would just say we need to, in conclusion, we need to think broadly about distributed learning. Federated learning is just a very basic, primitive federated averaging technique that is useful nonetheless, but not a panacea. There are also issues of deep learning versus or any black box techniques versus other techniques. Black box machine learning techniques are hard to explain, as we all know, and that is a major issue when we try to deploy these for operating, say, optimizing networks or for any kind of business problem. No one is going to be comfortable having a black box model control some critical infrastructure and so on. So what can you do without black box techniques? And how do you federate them? How do you apply them when data is distributed? So we need to think about all of those issues, right? So these are some of the papers that you can go look at and reach out to me if you're interested in knowing more. So let me pause here and we can go into Q&A, I guess.
Thank you very much. So also thank all the panelists for the great talks. So unfortunately, we are running a bit late because the technical difficulty we have run into. So we'll have about 20 minutes that we can actually have some discussion. So we're going to open up the floor, and we're going to just use Ethernet protocol, right? So do collision detection. Anyone want to talk? Just can.
Okay, I'll start with a question. Both Sumi and Nirmit mentioned the importance of selecting the most suitable data, right? So I'm wondering, how is this, can we use the traditional active learning techniques, or are there additional challenges that we need to address? I think that's a very important point, especially in network setting. Very
good. So I would answer that by saying that active learning is definitely one of the useful techniques in that context. And it's if you can apply active learning in a distributed setting, then I think that's useful. But there are many other techniques. There is something called core sets, where you identify a much more compact representation of the data set at a given location. That is, it is very intuitively, it's very similar to data compression, but you're compressing your data cognizant of the downstream processing. So if I'm going to apply an iterative neural network processing after I compress my data, then I would compress it differently than if I were going to apply Bayesian neural nets. So that is one of those opportunities you have, both opportunity and challenge you have when you have distributed environments. So.
Great. Any other one who have any questions?
Yeah, I have a question. Okay, this is Tamer Miriam. Thanks for this interesting discussion. I have just a general question, especially since the panel is from both academia and industry. When I compare like our community, networking community, with other communities like maybe computer vision, where they use AI, machine learning extensively, they have the concept of like some benchmarks. They share data. They have some kind of standardizations, even implicitly, and that's how they collaboratively add into that field and building on top of each other. Unfortunately, our community, networking community, we've been working for a while as an isolated island, and we don't have any benchmark. Everyone comes with his own data, his results. And now I see that we are, as a community, trying to change this by adding these reproducibility and all these tags on the paper so that the data available and all the things. Now I'm talking from the perspective of AI or using AI in networking. Do we really need to come up with something like that adapted in other communities to advance that field? Because, or otherwise, how do you see this will results if we continue as isolated efforts here? Is my question clear? I hope it's clear.
Yes.
You want to?
I don't know. Someone wants to go first.
Well, I could, I have a short comment about that. Yes, the need for something like an ImageNet for say specific problems in networking has been felt, and it's been discussed for a while. But I don't see how far along. I don't see the community as having made much progress in generating something like an ImageNet.
Yeah, following up on that, I think one particular challenge we have is in networks, we have very diverse problems that goes from physical layer to application layer. And for some specific problems, we do have some data sets. For example, we worked on encrypted traffic classification. There are some data sets that we can use, as well as we also collect our own and share our own. But for some other problems, the data sets becomes much trickier, especially if we do some kind of control. Then you have to implement your control policy in the real network to get an output, to get a real trace, useful trace. Then if someone has a different algorithm, potentially it needs something different. I think we need, first, I think the problems we see, there's a huge dimension in terms of different types. For example, we're not just classifying images. I think that's one challenge. Another challenge is a lot of the work we do involves control or change of the state and action. I think these are two challenges I see. I don't have a good solution, unfortunately.
I wanted to just say that we absolutely need something like that. Like there is, we have, I think community, in the network community, in my view, has created very good simulation and testbed environments over the years as we have progressed. So if we had a 5G community-based simulator effort on which you could then say, let's say kind of optimizations that Sumi was talking about and others who have created them. Let's test them on this simulation environment and measure important things like what degree of automation do they offer, because that's a very important focus in the industry. Both Sayandev mentioned it, and I've seen it as well. Degree of automation in managing these complex networks is going to be essential. If you can maybe, just like ImageNet focused on object classification or image classification challenge, and that kind of bootstrap the entire community. maybe we start with something like this. It would be really good. I think it's an opportunity for the community.
I have a question.
Can I
yes,
just add?
so Sumi, you can first.
Yeah, because this is a very, very important question, actually. I like it very much. And I would agree with Shin, it's more complicated here in networking. But I would agree still with Nirmit that we have to do something about it. If we look at the use of 5G, for example, yeah, it is all over the place, but we can look at categories of application. Like we can look at autonomous vehicles, for example. Autonomous vehicle on downtown setting or a city traffic context, it can bring in some closure or some kind of focus where we're really able to set a benchmark to compare against. If we look at also IoT, IoT or 5G for IoT in general, similar things can be done where we're looking at the use of IoT in a home or in homes to set a benchmark for it. So I think it's something that's crucial. I think the complexity is high, but we should at least aim to get some of the application spaces covered.
Great. So you have a question?
Yeah. So Professor Sami talked about that we need to do machine learning over the least most influential data. So we know that for traditional machine learning like decision tree or SVM, that this model need some feature engineering, feature selection, feature extraction. So do you think that with deep learning, this step of pre-processing help to improve the model or not?
So anyone want to take on the question? I think the question is traditional machine learning, you need to do a lot of feature engineering. Now with the deep learning, whether that step is actually, you don't have to do feature engineering, right? So is that correct question?
Yes, for deep learning, how we can choose the right feature or the right data or the most relevant data. So this is the question.
Mm-hmm. Right.
I have a quick and only partial answer to that question. It might not be a full answer. Basically, yes, in theory, in deep learning, you let the network itself extract the features that it needs. But in reality, I think what we are doing is just punting the problem from, human curated feature extraction to actually a problem of network architecture selection. Because if you choose the wrong architecture for your neural network, you're probably not going to be able to extract the right features, and therefore performance will suffer. And the neural architecture search problem is itself quite a large, research area, very active. There are new papers being published practically every week, claiming some minor improvement in performance over something else. But I don't think the need for feature extraction in some form has gone away. It's just that it's been abstracted now into something like choosing the right neural architecture.
Yeah, I would mostly second that. It's a common, just in practice, you'll find that you don't have the luxury of having millions of images like you have in the visual recognition challenges. Visual recognition is not one of the most important problems to solve for the world. So you go back to the roots and the fundamentals of choosing the right features, choosing the right amount of data, dealing with the fact that you don't have sufficient amount of labeled data. So I think the premise that neural networks relieve you of having this solving this problem of feature selection is only true if you assume infinite resource and infinite data, which you're never going to have.
And
Go ahead.
Just add to that. I agree with what has been said. It requires a lot of data. It requires potentially network architecture search. If you have a problem that has a fair amount of data, and it's kind of a classic type of problem. You might be able to get away, but it really depends on your application. So I'll just give you an example. A student of mine worked on using sensing data to identify ICU patient movement. It turns out in that case, they were able to just use a neural network end to end. But in other cases, you absolutely need good features and right data and possibly the right architecture. So it really depends on your application, I think.
Okay, so I could have a question that's kind of related to what has been asked, right? So you kind of, people have asked about the data set. We don't have enough data set. And the second problem is, I mean, one of the issues actually not just the data. Right? So in networking actually is a data-rich environment. You can just collect whatever data. It's actually labeled data, right? So some form of ground truth. So that's one. And for example, Xin, you were talking about the cellular network configuration. In fact, I work on a similar problem. In fact, a lot of this cellular base station provides you all kinds of counter meters. Right? Try to use it to solve some specific problem actually were hard. You actually don't really know what data to use, the meaning of that. Right? So the question kind of related to this one. One is we need to definitely be able to get a better data set. The second question is also think I'm kind of interested in looking at how machine learning also going to change the way we design the network, architect the network. So I think some of you actually touch on that. Is that, for example, the way how we actually even what type of data we're going to generate, counter, etc., going to be different instead of just kind of blindly setting all the counters and output a lot of data. In particular, as I think Nirmit talked about in the term of feature selection, we can't really spend a lot of kind of computing resources try to figure out what is the right data, right? So because we also have a control problem, we need to make decisions really fast. So have you guys thought about how we should architect the network differently because of we're going to apply machine learning to some of the problems?
That's yeah.
I think, Nirmit, you are muted.
Oh, am I? Can you hear me?
Oh, yes.
I can hear you.
Sorry. Just a quick note. That's a good point. You know, so far we have talked about applying AI to solve some of the networking problems. Well, there is the other side as well, and that is one of the things that we have run into is that with 5G, especially with network slicing and so on, and knowing that, let's say, if the network is aware that an application is running a federated learning process across a large number of websites and they're going to share model updates from time to time, allocating the right network slice and right network resources to support that, as opposed to something that is very urgent, say an ambulance is driving through the road and is streaming telemetry data, it has a patient in it, data is being streamed to a hospital where doctors are watching it and taking some actions or whatever. You want a very different network slice for that. So I think figuring out, I think network is definitely going to enable a smarter AI workload orchestration or what to call it. I don't have a name for it, but it's going to be important to look at the other direction.
Yeah, I agree with that. And also just add to that, I think Zhi-Li has a really interesting point. If we are going to apply machine learning widely in networks, how do we make this easier and more feasible? I don't have an answer to that. Just to add to this question, I think what kind of abstraction, I think one thing is definitely API that we can provide to upper layer per se, or even external developers to use data that's available. Another question I find is really challenging is what level of abstraction, because as Zhi-Li said, there's huge amount of data in the network. We just can't save all of them and share all of them, right? So what is the right level of abstraction in subsets? How do we do feature selection or data compression I think those are really interesting questions we should look into.
Any other has anything to add in? Even though anyone in the audience can actually chime in.
Yeah, I have a couple of questions or comments. Well, first, I would like to thank all the panelists. This is a very interesting and very important discussion I think we should have in the community. The first comment follows up on what Tamer has suggested and Sumi and Nirmit and others regarding this community resource of a library. And I agree that we've done a decent job for network simulation. For example, I was part of the NS2 project. And then you probably know about Crawdad and Mobilib that have made many data sets available. Although this is a start, I don't think it's enough. So, I mean, we should probably have a resource of benchmarks to tell people when is enough data available. What is the right data and the right features? And again, these are very, very hard questions to answer. So that's the first question or comment, and maybe people can jump in. And I agree with the Sumi comment that probably we should focus on certain communities and start from that. I think either a big effort will come from above and suck the community that way, or, and my preferred approach would be to have a grassroots effort from people collecting and sharing data at a personal level, and then that, you know, brings people together and so on. The other question I had specifically probably for Sumi, where he had this very interesting idea of processing the sensed data before you send it, which reminds me in sensor networks of in-network processing, but it seems that the idea that Sumi is proposing goes way beyond that. We are trying to do what I would call optimized sensing on demand. And the question is, you know, who will do the optimization? And are we going to continue chasing the optimal solution, and at what cost? And what is the benefit for that? So these are my two questions or comments.
So also just a kind of jumping comment. So this is the end of the workshop. Do we have time to continue a few more minutes?
Yeah, absolutely. Yeah.
Yeah.
No problem. Okay. Sumi, you want to answer the question?
Yes, I think for Ahmed's first comment, I echo the same point that Nirmit actually made it clearer, which is to look at network slicing. We can actually do this benchmark, approach the benchmark slice by slice, and the slices are focused enough to sort of combat the complexities in them. So I feel warmer actually to the idea that we do need benchmarks. We don't have to chase this in only network conferences or venues, but we just need to find the right venues and sort of evangelize to get these things done, because certain communities actually may have a faster way of generating data than others. So we shouldn't stick only to network conferences and forums. So I think it's a great idea. It's a great effort that can, if it's put together, I think we'll all benefit from it. The second point raised by Ahmed is the idea of doing this selective sensing and delayed sensing. When delayed binding and all the stuff, that are old concept in operating system. Like, wait, you may not have to do anything. So the idea is not only wait and not have to do anything, but also where to do it. The data comes from a device. Maybe the application need to come and descend closer and closer and even contain that device. By containing it, latching on it, data will not fly at all until the interesting data comes out. And maybe then you're able to go back to your applications. So it is moving, it is a constraining movement of all data and stuff, but also it's about the old ideas of in-network computing, more specifically where the computation happens. The network is so fluid now, computation can happen in any place, even on the device itself. So we need to be ready to understand the real cost of analysis, of data. Data is great, but it comes at a big cost. I particularly point to the energy cost, because if the whole world go into these devices to get the data to understand what's happening in the world and understand it very well, well, that's great. It's a great cause in itself. But I can assure you that these devices will not last long, because then everybody's coming to them, because they have the secret sauce. They've got the data. Everybody go to them. These devices will not last. So we have to find a way to just fend off all this demand on data, just tame the hunger of the machine in a way.
Thank you.
Can I ask a question if time?
Sure.
So you have talked about the federated learning. So I want to ask about the use of federated learning with network slicing. So what do you think about this?
I think it's an interesting combination. There is definitely value in studying how slicing can support federated learning better. I mean, that's one way of looking at it. And I don't think it's a problem that has been addressed. So if you were to come up with some kind of an optimization technique that that implements some kind of SDN policy to cater to the applications like federated learning, it would be very valuable. It's going to be, federated learning is going to be widely applied, and you're going to solve an important problem if you look into it.
Thank you.
Zhi-Li, I don't know if there's time for one more question.
Sure.
I want to ask everyone here to share what are some successful stories of using machine learning in networks.
Good question.
Inspire more research in this direction.
Right.
So you talk about more kind of real life, not just
not just
examples, right?
Young paper.
Yep.
So maybe I can start. So one of the things we've done is in network root cause identification or problem determination kind of a thing, looking at network and system logs. Okay, so you have many network components, and many IT components, and they're all operating, and some things are running slow, or some connectivity is lost, or any of these common issues occur. You want to find out what's the root cause. And all of these components are generating unstructured, semi-structured log statements, which tell you a lot about what might have happened, only if you can make sense of that. So that's one example where we have deployed this in multiple IT environments successfully, and it drives much greater automation in problem determination and root cause analysis space.
Nice.
Yeah, one example I can give is from my previous employer, where they actually did RSRP prediction. So it was in order to facilitate handover. So the idea being that you want to get an accurate prediction of what RSRP will be from a certain base station or set of base stations at some future point in time. The benefit of focusing on RSRP is that the data is always being collected and it comes labeled naturally. So you don't have to do anything except wait, in order to get the ground truth. And so it was the main problem there was a neural architecture selection problem. Because it's not one of the conventional things. It's not a really time series prediction, not exactly. It's not image classification, of course. It has some aspects in common with both. And to choose the right architecture to solve this, well, every architecture search is essentially ad hoc and heuristic. So that's what consumed the majority of the effort of the team for over several months.
That's really interesting. Yeah.
So maybe this is a good time we actually conclude the panel. Let's thank all the panelists.
And thank you for organizing, Harshit, for organizing it.
Thank you very much.
Yes,
Thank
you
you
all.
Otherwise, I think we can continue the discussion forever.
Very much.
Tamel, you can actually take the control and conclude the workshop.
Thanks, Zhi-Li, Harshit, and of course all the panelists. It was a very interesting discussion, and I think maybe next time if we organize something like that, I would love to have more time for the panel because there is a lot of questions that I prevented myself to ask actually. So I think this is conclude the workshop, the HDR-Nets workshop. Please, if you have any feedback, any suggestion, feel free to reach any of the organizing committee to just send us an email about that. If you'd love to see that this workshop to next year too, that would be really great if you have any comment about that. Other than that, I will give just a big applause for everyone, for the organizers, for the speakers, the presenters, the authors, the panelists, everyone even who attended the workshop. Thanks a lot for having this till the end of the day. I know it's too late in Europe. Far East, I think they're already sleeping. So it's really tough with this time zone, but just a big applause for everyone who participated and make this successful workshop. Thanks a lot.
Thanks,
thank you.
Thanks.
Thank you.
Thanks, everyone.
Thank you.
Stay safe and hope you enjoy the rest of the ICNP conference, the main conference that's starting tomorrow.
Thanks.
Thanks, Leonard.